Welcome back, focused learners, to another explainer. Now, if you've been working your way through calculus, you already know the ins and outs of taking derivatives. You're totally comfortable breaking things down to find rates of change. But today, we're diving into Lesson 19, and we're going to approach integration a little differently. We're not going to treat it as some entirely new, completely alien language. Instead, we're going to look at it simply as the vocabulary of differentiation, just spoken in reverse. Okay, let's jump right in.
I want you to ask yourself a question. What if you could run calculus entirely in reverse? Seriously, think about it. When you take a derivative, you're creating a finished product, right? A rate of change. But what if we took that finished product, broke it apart, and tried to figure out exactly how it was built in the first place? That is the essence of reverse engineering. And honestly, that's exactly what the whole process of integration is all about.
Here's our roadmap for today's explainer. First, we'll meet the antiderivative. Then we'll master the power rule, tackle trig and the chain rule, learn exactly how to check your work, and finally take on the bonus challenge. All right, section 1, meet the antiderivative, undoing the derivative. So what is an antiderivative? It's basically a function whose derivative gets you right back to where you started. Think of the original function we're trying to integrate as a crime scene, and it's our job to find the original suspect. But there's a catch here. Whenever you find an antiderivative, you absolutely must add plus c at the end. Why? Well, because the derivative of any constant number, whether that's 5, a million, or -12, is just 0. So when a function is differentiated, any constant gets completely wiped out. When we build the function back up, we have to add that plus c to represent the ghost of constants past. It's kind of like our mathematical placeholder for whatever might have been there originally. To take a derivative using the power rule, you multiply by the exponent and then subtract 1. You've done it a million times. So to go backward, we literally just reverse those operations in reverse order. For the antiderivative, you add 1 to the exponent first, and then you divide by that new exponent. See? It's the exact same mechanics you already know, just shifted into reverse gear. Moving right along to section 2, mastering the power rule, leveling up with fractions and roots. Let's see how this works with some actual problems from the Lesson 19 set. Take problem 1, the integral of 2x minus 3 dx. Because integration is linear, just like differentiation, we can tackle this term by term. We can even pull constant multipliers right out of the way. So let's look at the 2x. The x currently has a hidden exponent of 1, right? We add 1 to get 2, then divide by 2. The 2 we started with and the 2 we divide by just cancel each other out, leaving us with a clean x squared. The -3 is a constant, so its antiderivative is simply -3x. And of course, we can't forget our ghost of constants past, plus c. Putting that all together, our final answer for problem 1 is x squared minus 3x plus c. Bam! Simple, elegant, and directly reversing the power rule. But hey, we all know calculus isn't always pretty whole numbers, right? So let's look at a tougher one. Problem 2 has some pretty intimidating fractions. We've got the integral of x to the 1/2 minus 3x to the 11/17 plus x to the -2. Now, the absolute crucial point here is the rule does not change. We still integrate term by term. For x to the 1/2, add 1 to the exponent to get 3/2, then divide by 3/2, which, remember, is the exact same thing as multiplying by 2/3. Moving on to -3x to the 11/17. Just add 1, or 17/17 to the exponent, which gives us 28/17. Then divide by that, meaning we multiply our -3 by 17/28. Finally, for x to the -2, add 1 to get -1, divide by -1, and it just becomes -x to the -1. Slap a plus c on the end, and boom, you've completely beaten those ugly fractions using the exact same basic rule. Okay, but what happens when a problem throws a root at us? Like problem 3, the integral of 3 times the square root of t plus 1. The secret here? Just rewrite the thing before you even touch the math. First, rewrite that square root as a fractional exponent, 3t to the 1/2. Now it looks exactly like what we were just solving. We add 1 to the exponent to get t to the 3/2, and then divide by 3/2, which means multiplying by 2/3. The 3 we started with multiplying by 2/3 just leaves us with 2. That plus 1 at the end, that becomes a plus t. And we finish the whole thing off by adding our plus c. So the final answer for problem 3 cleans up beautifully to 2t to the 3/2 plus t plus c. By just doing a quick rewrite of the root, we unlocked it using the exact same power rule mechanics. All right, let's step up the difficulty. Section 3, trig and the chain rule, reversing the ripples. Think back to differentiation for a second.
When you take the derivative of something like sine of 2x, the chain rule dictates that the derivative of the inside, that 2, pops out to multiply the whole thing. It becomes 2 cosine of 2x. So logically, when we're trying to find the antiderivative of something like cosine of 2x, we have to do the complete opposite. We must divide by 2 to undo that chain rule. Problem 4 asks us to integrate 2x minus 3 cosine of 2x. The 2x is super easy, that just becomes x squared. But for the minus 3 cosine of 2x, the antiderivative of cosine is sine. And because of that 2x inside, we have to divide by 2.
This means our final answer for problem 4 is x squared minus 3/2 times the sine of 2x plus c. Look at that! We successfully integrated a trig function and cleanly reversed the chain rule, just by remembering to divide instead of multiply. Which brings us to section 4, checking your work, the ultimate background check. Now, if you're ever unsure about your answer, this next method is an absolute game changer. I love this concept. Integration isn't complete until you differentiate your suspect to see if they match the original crime scene. Because we are literally just reverse engineering, we have a built-in quality assurance tool. To prove we integrated correctly, all we gotta do is take the derivative of our answer. Let's actually test this out on our very first problem. We take our calculated antiderivative, which was x squared minus 3x plus c, and simply take the derivative with respect to x. The x squared becomes 2x. The derivative of negative 3x is negative 3. That constant c, it goes straight to 0. And what are we left with? 2x minus 3. That perfectly matches our original integrand from problem 1. The suspect is a match. Seriously, you can and absolutely should do this for every single integration problem you solve. Okay, section 5, the bonus challenge, the boss level. That powerful checking tool we just used, it brings us perfectly to the final boss of lesson 19. The problem set throws a bit of a curveball at the end. It says, the solution to finding the antiderivative of an unknown function, f of x, turned out to be sine of x minus x times cosine of x plus c. So what was the original function, f of x? Now, at first glance, this looks like a massive integration mystery. But here's the brilliant insight. We don't actually need to integrate anything at all. We already have the answer to the integration. To find the original question, the integrand, f of x, we just use our background check method. We simply take the derivative of the right side. And to do that, we gotta dust off the product rule for that x times cosine of x term. Let's walk through it carefully. The derivative of sine of x is just cosine of x. Easy enough? Then we use the product rule on the chunk that is x times cosine of x. The derivative of the first term, x, is 1, multiplied by the second term, cosine of x, plus the first term, x, multiplied by the derivative of the second term, which is negative sine of x. That gives us cosine of x minus x sine of x. Finally, we subtract that entire chunk from our first derivative. We get cosine of x minus, in brackets, cosine of x minus x sine of x. You gotta really watch your negative signs here. The cosines cancel each other out, and the double negative on the x sine of x turns it positive. And just like that, the dust settles, and our final answer for the bonus is revealed. The original function, f of x, was literally just x times sine of x. We found an integrand not by integrating, but by remembering that integration is just a two-way street with differentiation. So, as we wrap up this explainer, I want to leave you with this thought. If integration is simply the vocabulary of differentiation spoken in reverse, what new worlds does this open up for us? Think about it. If differentiation allows us to find the exact speed of a rocket at any given moment, integration allows us to take a messy, chaotic log of speeds over time and perfectly reconstruct the exact distance that rocket traveled. It means that literally anything we can break down, we can build back up. Keep that in the back of your mind as you tackle your next problem sets. Keep running your calculus in reverse, keep checking your work, and I'll see you in the next explainer.